record this. You can have a gas in solution. Hence, you have something that's a carbonated drink. Okay. Or you can have a liquid in liquid, like a mixed drink. Okay, that's a solution. Also, you can have the obvious one that we're all familiar with, a solid in a liquid. For example, table salt, you pour it into water, you create salt water. Another example of a solution where you have a solid in a liquid. Or you can have gas in a gas. Our air is a solution. And where we have a mixture of gases in there, nitrogen, oxygen, carbon dioxide, and a variety of different gases. But you're not limited to just that. You can have a solid in a solid. Things like steel. Steel is not pure iron. It's made up of iron and some carbon to give it strength. Another example would be gold. Our earrings and rings and so forth are not made of pure gold, because pure gold in itself is very soft. So you add other things in it to strengthen it up. So here's some examples of different types of solutions. Okay, now the key thing about solutions is to remember this, that like dissolves like. So it goes back to polarity. Okay, so polar solutes dissolve in polar solvents. Okay, polar dissolves in polar. The contrary to that, the opposite of that is nonpolar solutes dissolves in nonpolar solvents. Okay, for example, try to mix table salt and oil. It's not going to happen. Okay, because table salt is very polar, oil is very nonpolar. Okay, and we know that nonpolar and polar do not mix at all. Taking a good example is that picture in the bottom left corner where you have oil and water. Big mess. Okay. Now, when we talk about liquids mixing, we use the term miscible. When two liquids do mix, because they're both polar or they're both nonpolar, that is called miscible. When they don't mix, the term used is immiscible, only for liquids and liquids, okay? So key to remember is like dissolves like is the rule. We all know that oil and water do not mix because of the difference in polarity. Now, when we talk about solids in dissolving in the liquids, we use the term either soluble or insoluble. So if a solid dissolves in the liquid, it's soluble. If it doesn't dissolve, it's classified as insoluble. Refresh your memory with respect to the solubility rules, okay? In the solubility rules from the periodic table, things were either soluble or insoluble. Now, being insoluble doesn't necessarily mean, if you remember, that it's 100% insoluble. There's a little bit in solution, small amount, but the majority of materials is not. Now, you might get a table like this and to look at to determine whether the solute, which is on the top of the column, will dissolve in these solvents. You have three different solvents. NH3, otherwise known as ammonia, and then you have C12H26. Now, you may not know what that compound is, and that's okay, but I hope you can recognize that that particular formula consists of nothing but carbon and hydrocarbon. And then we have bromine in the bottom left corner, okay? As the solutes, we have HCl on top, and then we have iodine, and then we have phosphorus trichloride, PCl3, and then another hydrocarbon, CH4, otherwise known as methane. Now, before we can decide if they're going to dissolve, you have to first determine whether that molecule is polar or not. Top left corner of solvents, we had NH3. Recall that we worked that with respect to Lewis dot structures ended up with a lone pair on the nitrogen, which automatically tells you we have a polar compound, okay? C12H26. Like I said, we may not know what it is, but we recognize that we have nothing but carbon and hydrogen there. Hence a hydrocarbon. And recall that a carbon-hydrogen bond is nonpolar. Therefore, this species, regardless of what it is, chemically, is a hydrocarbon, but it's nonpolar. Okay. And then we got Br2. Okay. Recognize that again, that is a diatomic molecule of bromine. Diatomic meaning that that bond is nonpolar, so that species is nonpolar. Going across to solutes, HCl, well, we have two dissimilar atoms connected, automatically polar compound, with the exception, remember, carbon, hydrogen. But anything else, polar compound. So hydrochloric acid is polar, okay? And then we have the solute iodine, I2, again, diatomic molecule, nonpolar, okay? Finally, the PCl3, if we do the Lewis-Nash structure, it's very same structure as ammonia, lone pair on the phosphorus, automatically polar species, okay? And then the last one, CH4, again, carbon, hydrogen, nonpolar bonds, nonpolar species. Now, with that in mind, once you define what the molecule is as far as polarity, now it's a simple matter of remembering like dissolves like. So we had the first one with ammonia and hydrochloric acid. They're both polar. We're going to get solubility. Next one is nonpolar with ammonia, no solubility, and it won't dissolve. Next one, PCl3 with ammonia, obviously both being polar, yes, we're going to get solubility here. It will dissolve. And then finally, the last one, no solubility because they're dissimilar with respect to polarity. Next solvent down, the hydrocarbon with hydrochloric acid, no solubility. Next one, yes, because they're both nonpolar. We're going to get a no for PCl3 in the hydrocarbon, again with polarity, because of polarity. And then finally, the last one, yes, because they're both nonpolar. Bromine being nonpolar, hydrochloric acid, no solubility. Bromine with iodine, yes, they're both nonpolar. And no for the next one because of polarity. And finally, yes, okay? So the takeaway from here is define what the molecules are, polar, nonpolar. That in itself would tell you whether one would dissolve in the other. Okay. Now, the same is true with liquids here, obviously, when we talk about polarity, but the difference is we use the term miscible and immiscible for liquids, insoluble and insoluble when we're dealing with solids and liquids. So the first one, we would call that miscible because we have a polar liquid and a polar solid. And immiscible because we have a polar liquid and a nonpolar solvent. Good example there would be oil and water. We know it doesn't mix, two separate layers. Nonpolar liquid, immiscible. Nonpolar liquid and nonpolar solvent, miscible. Now we have a polar solvent and a polar solvent. Yes, it would be soluble. With nonpolar solvent, we label that as insoluble. Nonpolar solid and polar solvent, insoluble. And soluble when we're dealing with two nonpolars, with a polar solid and a nonpolar solvent. With respect to ionic solid, well, it depends. You know, we first have to remember ionic solid would imply metal, non-metal, okay? And we dealing with a polar solvent, we check the solubility rules to find out if it's classified as insoluble or insoluble. And then obviously with ionic compound, which is very polar, okay, and a nonpolar solvent, totally insoluble. All right. Now, the dissolving process, we briefly touched on this previous chapter, but basically because of the polarity and the dipoles involved in the solvents, you can see here that water molecule here has a partial negative due to the oxygen, so it's going to interact with the sodium ion. If we had a chloride over here, this was sodium chloride, for example. Oh, that's supposed to be Cl. You got a negative charge, we're going to have interaction here. Okay, so this whole mixture will be dissolved by water with sodium chloride. And basically what's happening here, the solvent molecules, they will pull the solute molecules from each other if the solute-solvent attraction is greater than the actual solid being held together. And that's why things like sodium chloride in the solid will dissolve very readily, especially in water. Okay. Let me clear this mess here. Okay. Now, in solutions, we're going to deal with two types of concentration as far as calculations. The first one is called mass percent. And it's basically a weight divided by weight ratio times 100 to give us the percent, or the mass percent. Molarity has the units of moles per liter. Okay, moles per liter. So recall how we calculated moles. Different color here. Recall how we calculated moles. To calculate moles, you start with grams. You got to divide by the molar mass. How do we calculate the molar mass? We add up all the atoms associated with that compound to give us the molar mass. Okay, and then the units in the denominator are liters. Sometimes you're given the problem in liters. Sometimes you're given the problem in milliliters. So you need to convert the milliliters to liters. And recall that in 1 liter, there are 1,000 milliliters, okay? So molarity with a capital N. Also a concentration unit. It's just a different type of concentration unit than mass percent. Yeah, let's do a couple. All right, let's take this example here. It says calculate the mass percent for 15 grams of potassium nitrate being dissolved in 135 grams of water. Now, first thing, when we're doing mass percent, we don't have to be concerned about the molar mass, okay, because it's a mass relationship. Point number one. Point number two is the mass of the solution. That incorporates not only the mass of the liquid, in this problem here it's water, but also the mass of the solute, which is in this case potassium nitrate, 15 grams. Hence, in the denominator, we have the sum of both those weights, 15 grams and 135 grams. And in the numerator, we just simply have the mass of the solute, which is 15 grams. So that ratio there, after you do the math, you multiply it by 100, you end up with a 10% solution by weight. Okay, so taking 15 grams of water, dissolving it in 135 grams of, 15 grams of potassium nitrate, and dissolving it in 135 grams of water gives you a 10% by weight solution. Here they use potassium nitrate, but in reality it could be anything because we're not concerned about the molar mass here. We just want to know how much of that material we're going to be using. All right, so occasionally, oh, I messed this up. The question is this. They're asking you, how many grams of water? The previous example, they gave you the amount of grams, okay? But they're asking you, how many grams of water do I need to make a 5% solution with 10 grams of salt, any type of salt, okay? And so to do that, we set up the problem as follows. Okay? We're given 5%, that's what we're striving for. We know that this quantity here, when we multiply by 100, gives us the percentage. What we don't know is the grams of water, and therefore we define that as X. Okay, so we're going to do a little bit of algebra here, not too complicated. We got to figure out how much water we're going to need to make a 5% solution if we have 10 grams of water. Okay, so being an algebraic equation, there's multiple ways to solve this. This is just one way. So let's take the first one. Okay. Well, you see what they did here? They're trying to isolate to refresh your memory in algebra. If you got it, if your algebra is okay, then no worries. But to refresh your memory, what they did here, they wanted to get rid of, they multiplied both sides of the equation by the quantity of 10.0 plus x on both sides, which means it gets canceled on the right side and it ends up on the left side, okay? So now at this point, you can, like I said, you can do this in a number of ways, but what they did here was went ahead and multiplied the 10 times 100 to give you 1,000, okay? Next step was they got rid of the 5 on the left-hand side and put it over here on the right-hand side. And they did that by dividing through by 5 on both sides of the equation. Okay, which simplifies the equation even further. So now they took 1,000 divided by 5, they end up with 200 on the right-hand side, and we have 10 plus x. We want to solve for x, and so we can subtract 10 from both sides of the equation, leaving us with 190 grams. They put it in scientific notation because of the sig figs. So what this tells you here, that you need 190 grams of water plus 10 grams of salt to make a 10% solution. Now, what do we do to verify that that's the case? Well, you take your number and you plug it back in the original equation. And if you do that, you end up with 5.00 on both sides of the equation, which means, yes, you solved it correctly. Obviously, if you do, you can come up with a different number, then check your math, or maybe, just check your math someplace somewhere. Mathematically, you just made a mistake, okay? But if it ends up 5 equals 5, then that's the answer. It's just a check. All right. Let's clear my stuff here. All right, so molarity. Okay, so what we just talked about was mass percent. Either we're going to be given the water amount and the solute amount, or maybe we need to solve for the water quantity. In this scenario, you're asked to calculate the molarity, moles per liter. Okay, and so here's the problem. Saying calculate the molarity if 9.99 grams of potassium bromide is dissolved in water to make 2.5 liters of solution. Okay, now here's a couple of things. Recall molarity is moles per liter, so we're good on the volume. It's in liters units, okay? But we need to calculate the moles of potassium bromide if we have 9.9 grams of potassium bromide. Well, in order to do that, we need the molar mass of potassium bromide. And before you can do that, you're going to make sure you put it together correctly in the formula. And so by the name potassium bromide, you know that potassium ion is a +1. It's in group 1. When it becomes potassium becomes an ion, it'll be a +1. The bromide is in group 7. Bromine is in group 7. When it becomes bromide, it picks up an electron, so it has a negative charge. So structurally, I need 1 potassium, 1 bromide, which gives me the formula KBr. Okay. Once I know that, I add up the atomic weights for potassium, the atomic weights for bromide, and I have its molar mass, which is 119.00 grams. Okay. And now I can calculate the number of moles because I'm given 9.9 grams. Notice I set up the ratio properly. That molar mass can be set up one or two ways, if you recall. Look at my units, my grams cancel. Okay, leaving me with the units of moles in the numerator, which tells me I set that up properly. Okay. Now it's a matter of taking that number, dividing by the volume given. Okay. And so now my molarity for this solution is 0.0336 moles per liter. Okay. So if I weigh out 9.99 grams and I dissolve it at 2.5 liters of solution in water, my molarity would be 0.0336 moles per liter. Okay. All right. So the takeaway from this part is, if you're given this problem, you need to first be able to put the formula together correctly with the right number of atoms of each ion. Once you do that, now you can calculate the molar mass. And once you got the molar mass, given the number of grams of that material, divided by the molar mass gives you the number of moles. And then divide that by the volume. And if the volume is already in liters, you're good to go. Punch the number in, you got it. Keep track of your sig figs. If that value is given to you in milliliters, you need to convert that to liters, given that 1 liter equals 1,000 milliliters. Okay. Now there's in your practice worksheets, there's a lot of examples of this. I might, go back there and download the worksheets and work through them. Okay, use some more practice. Now in this case here, they're asking you, calculate the molarity if 5 grams of sodium phosphate is dissolved in 255 milliliters of solution. Okay, and they want molarity, moles per liter. Okay, so 2 things to see here. We got 255 milliliters, so obviously we're going to convert that to liters. That's 1 point. Second of all, I need to figure out the molar mass of sodium phosphate. Okay. Phosphate, if you recall in their polyatomic ion table, you will find phosphate there, and it has a formula of PO3 -3. Okay. Sodium ion, it is in group 1. So we know that when it becomes ionic, it will have a +1. So therefore, I'm going to need 3 sodium ions for every phosphate. So my formula becomes Na3PO3. Once I know the formula, I add up all the atoms, and I have a molar mass. Okay, so there's the formula. Okay, and 3 sodiums, 1 phosphorus, 4 oxygens should give you a molar mass of 163.94 grams per mole. Okay, we're given 5 grams. We divide by the molar mass. It gives us the number of moles of sodium phosphate. Obviously, there's a lot of numbers there. Keep all those numbers because you don't want to truncate until at the end with respect to your sig figs. If you notice, we started off with 5.0 grams is 2 sig figs, 255 milliliters is 3 sig figs, so our answer should have no more than 2 sig figs at the end. Okay. Since we're given a 250 milliliters of solution, we need to convert that to liters. And we have our conversion factor there. Again, another ratio, keeping track of my units. Okay, milliliters cancel. Now, if you remember, you can just simply move the decimal point over three decimal places, but if not, use your conversion factor, okay, to get you to 0.255 liters. Okay. Plug in the numbers, okay, you end up with 0.12 moles per liter. That is if I take 5 grams of sodium phosphate and I dissolve it in 255 milliliters of solution. That is the molarity of that solution. Okay. You know what? Guess what, folks? I told you it was short. Just a final few last words. I mean, don't forget the assignments that are coming up, and including the ones that maybe you missed. Go back and knock them out. Okay. There is uploaded already a practice final exam on the website, so I would download that. You'll find it to be very useful as far as studying for the final exam, which is comprehensive. Okay. Just a quick reminder: some of you have already sent me an email about the letter change P and Z. I made note of it. I responded to you. I'm keeping track of that because the grade is defaulting to P and Z unless you choose a letter grade. Okay, and just remember that May 1st is due date to get that decision made for you. That you need to make that decision. Now email me through Canvas just to make sure I have record of it. Okay. And then when I get that list and it's all completed, I will send an email with everybody telling them this is what you decided to do. And that way there's no question about it. What else? Next Wednesday will be my last Zoom office time. I've been here on Zoom for office time, but I'll be here tomorrow and Saturday, and next Monday, and then Wednesday will be my last one. Okay, so take advantage of that time. Okay, other than that, it's been a pleasure. I know it's been challenging for many folks having to change midstream, but given the circumstances, I suspect that we'll probably be doing a lot more online. I know this summer I'll be doing 1:30 again, completely online. So in the other courses, so you'll probably see a lot more hybrid courses, part online, part in class. So anyway, I want to wish you luck. If you have any questions, feel free to call me. Other than that, that's the end of chapter 15. Congratulations, you got through 15 chapters of chemistry. And those of you for showing up during the times here, I appreciate that. Thank you. Okay, any questions? You're more than welcome to unmute yourself and go ahead and ask or do a chat. No questions? All right. Well, I'll hang out here for another 5 minutes and then I'll go ahead and end the meeting. I'll record. This is being recorded, so I will get it uploaded sometime today. Okay. Take care. Did you have a question, Miriam?
Oh, no, I do not. Thank you so much for everything.
Okay. Well, you stay safe out there.
Thank you as well. Have a great day.